Hello and welcome to today's webinar. Thanks for joining. My name's Jamie Clayton. I'm Operations Director at Freeman Technology and I'll be your host and moderator for today's session. Today's presentation is on the measurement and quantification of caking in powders, and your speaker is Dr. Rajeev Dattani, who is Product Specialist at Micromeritics Instrument Corporation. Before I hand over to Rajeev and get underway with today's presentation, just some housekeeping tips for today's event. You'll notice that when you joined, you're in listen only mode. So if you do want to ask a question, you can use the question box in the On24 dashboard and submit questions there, or alternatively, you can send us an email if you have any more detailed questions or queries that you want one of our applications team to address. If you do send a question through the On24 dashboard, rest assured that it remains private. Other attendees can't see the questions. They're only visible to us as organisers, and we will do our best to address as many as we can in a brief Q&A session following Rajeev's presentation. If we don't get a chance to answer your particular question, then one of our team will be in touch in the next few days to respond to you directly. We've also made available some resources to download, so there's some application notes and some literature relevant to today's event available, as well as an attendance certificate if you would like one. When you leave today's session, there will be a very brief survey that appears, just a handful of questions, hopefully no more than a minute of your time, but we'd be really grateful if you could answer them. Just helps us to get a better understanding of the kind of topics that you'd like to see at future events, and make sure that we're delivering content that's of interest to you. If you have any technical issues during the presentation, feel free to put them in the Q&A box. We'll do our best to try and address any that we can. Alternatively, if you click on the help or the question mark icon in the On24 dashboard, you'll have access to some frequently asked questions, and you can also contact an On24 specialist directly via that route, who will be able to help with any more complex issues that you have. Today's presentation is one of a series that have been held throughout this year and also last year. So if you'd like details on upcoming events, please visit micromeritics.com/webinar, where you can find details of any future presentations, but you can also access recordings of previous presentations. On that subject, today's presentation is also being recorded and will be made available via a link that will be sent to you via email in the next few days. So again, you can watch that at your leisure, or please feel free to share with any colleagues that might also be interested. So on with today's event. As I mentioned before, your speaker is Dr. Rajeev Dattani. Rajeev is a product specialist at Micromeritics UK. Although prior to that, he spent 4 years working as an application specialist with Freeman Technology, based in our head office in Tewkesbury in the UK. So in that role, Rajeev had lots of exposure to powder handling challenges and powder processing issues that our clients around the world had. So he's worked with lots of different people in different sectors, different industries, different applications, learning about the challenges they have and helping them address them via use of the FT4 and powder rheology, not least including caking, which he's going to talk to you about today. Prior to joining Freeman Technology, he obtained his MSc in Microsystems and Nanotechnology from Cranfield University, which he then followed up with a Master's in Research in Plastic Electronics, prior to completing his PhD in Polymer and Fullerene Solution Processing from Imperial College London. So with that, I will hand over to Rajeev. I look forward to speaking to you all again in the Q&A session after his talk. Thanks, Rajeev. Over to you.
Hello, thank you for joining me today. So we're going to talk today about measurement and quantification of caking in powders. So how can we measure powder caking, and how can we start to quantify it? So powders themselves are used in a wide range of different industries, so pharmaceuticals, cosmetics, additive manufacturing, bulk chemical manufacture. And throughout all these different industries, we have thousands of different powder formulations. We have hundreds of different manufacturing processes that powder is expected to move through. And ultimately, what's key, regardless of the industry we're working in, regardless of the formulation itself, is the powder's characteristics that will influence how that material behaves in manufacturing. and in different unit operations, and ultimately will affect the quality and properties of the final product. But even though powders have been used in all these different industries for so many years, powder behaviour is still not that well understood, and that lack of understanding means we have stoppages, we have downtime, we have products that don't meet specification, and so ultimately it starts to become an inefficient use of resources. But if we can start to measure and understand powder flow and powder behaviour, we can start to overcome these challenges. So here we have an electron microscopy image of some powder particles. We can see we have some large particles with smooth surfaces, some small particles with rough surfaces. And it's very difficult to tell from this image how these particles as a group might flow in any given process. Yes, we can via imaging or other techniques, we can quantify size and shape distributions, but we don't get any detail there on how those particles might flow. Of course, we could have the more perfect case, the more idealized case of having smooth spherical particles, like in the image in the top right-hand corner. More realistically, there's likely to be a degree of particle size distribution and porosity, like the image on the bottom left-hand corner. And if we just look at this one individual particle that's on the image on the bottom right-hand side, we have a length scale distribution there. There is a pore size distribution as well, so you have some larger pores, you have some smaller pores, important properties to characterize for different purposes, but we won't get an idea of how that one individual particle will flow in any given process. And if we just take these smooth spherical looking particles, and if we zoom in with the microscope, we can see there is a degree of surface texture there. So we could be limited in this example, to what extent can we image these particles. And so each particle and each set of particles are defined by their own physical and chemical properties. So we've talked already about size, shape, surface texture, but the cohesive forces between the particles, the adhesive forces between the particles and a surface, porosity we mentioned, how hard are the particles, are they prone to undergo any attrition, what's the amorphous and crystalline content. And so each one of these properties and more will give some contribution to how that powder behaves in process. But powders aren't just the solid particles themselves. Powders are a bulk assembly that also consist of liquids, so usually water, that will be on the surface of the particles, and we have gas, usually air, between the particles as well, and of course that gas can contain some degree of moisture as well. And so powder behaviour ultimately is very dependent on how all three states of matter interact. So if you were to define powder behaviour and try and understand what that means, there's a whole range of different types of behaviours we could potentially be interested in. So powders will have a certain degree of compressibility, they might stick to different equipment or surfaces, powders will have a certain degree of permeability, a certain degree of attrition if there's any stress that's applied. And so there's all these different types of behaviours that we might be interested in quantifying. If we could define that behaviour mathematically, we could say powder behaviour is a function of its size, shape, stiffness, porosity, all those physical and chemical properties that I listed before, but it's also very much dependent on the environmental conditions which we expose that powder to. So for example, is the powder being consolidated? Is it aerated? What's the stress and strain that we put that out powder under? And what are the humidity conditions? And that's something which we're going to focus on throughout the rest of this presentation. But essentially, there's no way that we can just predict powder properties just from these first principles, just from these primary properties. If we had, for example, 12 variables and 4 permutations, this would give us over 16 million combinations. So mathematically, it's a very challenging problem to start to solve. So here we have a video of some powder particles in a vessel, and when they flow from one vessel to another, they might flow in a certain way. And in that process, air could get trapped between the particles. So if we now take this aerated powder, and if we pour that from one vessel to another, it might flow much easier in a more fluid or liquid-like way. And if we tap that vessel, so release the air from between the particles, so deaerate, consolidate the particles, that powder might not flow at all. So you can have the same physical characteristics of size, shape, and so on, but just by changing the packing state of the powder, we can go from a material that doesn't flow at all to one that flows extremely well. Other properties to consider as well, the surface texture, the shape of the particles, if there are any electrostatic forces between particles, if there's moisture on the surface of the particles that could lead to capillary bonding, and then also if the particles are friable, if they're prone to attrition, like we saw in a particle on the left, or if they're prone to any sort of deformation as well. And these particles, when they move up against each other, there could be a certain degree of friction that occurs between them. So, and again, that friction can lead to attrition as well. And there could also be a certain degree of interlocking that happens between particles as well. So when they try and move over each other, the particles might become locked and they're not able to easily slide over each other. Those electrostatic forces can also play a role in the particles binding together and the energy required for the particles to separate away from each other. And the topic of this presentation, moisture, so it's capillary bonds caused by the water due to the water being on the surface of the particles. So throughout that, I mentioned terms like high stress and low stress, but what's key is how that relates back to various processes and different applications. So to put that into a bit of context, if we have powder that's in a hopper, the powder at the bottom of the hopper will be under very high stress, and when you want powder to flow from that hopper, it will flow usually typically via gravity and in very low and well-defined flow rates. Alternatively, if we have a filling process, it's a much lower stress process. It could still be gravitationally induced flow, but it's a much more dynamic process compared to what's happening in a hopper where we're moving from a static to a dynamic state. Something in between the two, transport storage, so sort of moderate to high stresses. The powder could be susceptible to deaeration, to being consolidated, and also caking, so in long-term storage, for example. And lastly, we have aerosolization. So in process, we might see this as pneumatic conveying. In application, that could be something like dry powder inhalers, where the powder needs to fluidize to get from one location to another. And the point is that for any of these processes to be efficient, the powder properties have to match the conditions within that process. So if we take a bit of an analogy, and this is consider two athletes competing. We take our first athlete, tall, long stride length, they're very good at the long jump. We can take a second athlete, short, strong, very good at the shot put. So both of these athletes could be gold medal winners in their own events, but if we ask the long jumper to pick up a shot put, they might not be able to pick it up. And if we ask the shot putter to jump, they might not be able to jump. Now, have they become bad athletes? Because they still won gold medals in the events that they were suited to. But as soon as we asked them to do something different, they didn't have the ability to do it. The point is the properties of the athlete have to match the conditions which that athlete experiences in their event. And likewise, the properties of a powder have to match the conditions which that powder experiences within that process. So before we get started on the case studies that I'm going to present, I just wanted to introduce you to the FT4 Powder Rheometer. So this is an instrument that allows you to measure the dynamic flow of powders in confined and unconfined states, allow you to measure the aeration, permeability, compressibility of samples, as well as the shear properties, so by shear cell testing, and using the wall friction discs, the friction properties of the powder against different surfaces. So the various methods that we have available with the FT4, so we have bulk methods to measure density, compressibility, permeability, dynamic methods, as I said, to measure powder flow in confined and unconfined states, measure how the powder responds to being aerated or consolidated, as well as shear methods, so shear cell and wall friction. And with all these different techniques, we can then start to understand what's happening in process. So is there a degree of segregation occurring? What's the influence of attrition or agglomeration? And what we're focusing in on today is caking, and related to that as well is moisture. The main principle of operation for the FT4 for the dynamic methods, as this twisted blade will move up and down through the powder as it rotates. So as it traverses up and down through the powder on a defined angle and at defined speed. And what's measured there is torque and force as a function of height. The blade is used to move in two different directions. So in a clockwise direction, what we call the conditioning mode, the blade slices through the powder, so this thin edge of the blade will cut into the powder, so remove any areas of stress, remove any excess large air voids, and ultimately what we're targeting is a homogeneous low stress packing state. So you can see in this video here is the blade is moving through in that clockwise direction. The powder is being lifted up and then dropped back behind the blade, and that will happen throughout the whole depth of the vessel. Now if we reverse the direction of the blade, this flat surface of the blade will bulldoze down through the powder, so it's a much more aggressive flow pattern. The powder's compressed and compacted towards the base of the vessel. So you can see in this video here, the blade is now moving in the opposite direction. That flat surface of the blade is forcing the powder to move down and around through the vessel. And this is where we measure torque and force as a function of height. So as I said, we measure torque and force as a function of height. So as you might expect, the force will increase as we go down through the vessel, and likewise so does torque as that blade is rotating as we go down through the vessel. So how can we represent both torque and force in a single value? So that's the calculation of flow energy. So work done is force times distance, and we can then do a similar calculation for torque. So we can say force and torque times distance will effectively give us the flow energy. We can then also express this as an energy gradient, so calculate that work done for every millimeter of travel, and the area under the curve is then the total flow energy for that sample. And you'll see these graphs coming up later on in the presentation, so where we look at the energy as a function of height. But just looking at the flow energy in itself, so flow energy as a function of water content, as we add more moisture, we could expect more capillary bonding between the particles. There's more cohesive forces there between the particles, and it's harder for the blade to move down through the powder. As it's harder for the blade to move down through the powder, we see an increase in the flow energy. There's a higher resistance to flow. So now onto our first case study, the influence of environmental humidity and sample water content. So moisture is typically added into different processes on purpose, so for a reason. So for example, in granulation processes, it allows the particles to bind together, it increases blend and content uniformity, and results in typically improved tablet quality. You might also see this in milling and extrusion processes as well. However, occasionally there can be moisture due to the environmental conditions, so just due to the ambient humidity of in different climates. And anecdotally and typically, that moisture is sort of seen to be as something that's undesirable, something bad. This is because of potentially increased liquid bridging and therefore increased adhesion to different surfaces as well. But is this always the case? Does this always happen? So moisture could also help with electrostatics, so it could allow electrostatics to be discharged. Moisture can also act as a lubricant between particles, and therefore allowing improved flow. So really what we need to do is understand and quantify that behaviour between powder flow and how much moisture has been absorbed by the powder. So for this study, we took 5 different samples, so limestone with a smaller particle size of around 4 microns, typical lactose grade of Flowlac, microcrystalline cellulose at MCC or pH 200. We also had mannitol and sorbitol as well. The samples were held in a desiccator using with a saturated salt solution, so we're allowed to equilibrate for 48 hours. So the 5 different conditions used range from a relative humidity of 17% all the way up to 95% RH. So we could then measure how much moisture content was taken up by the samples as a function of relative humidity. So you can see, just to point out, that the sorbitol and the MCC are both on a different axis. So both of those materials took up much more moisture compared to the other 3 samples. So just to summarize that moisture content, so we have lactose and limestone that both had the lower levels of moisture content, closely followed by the mannitol. Then we have sorbitol at 2.5% moisture content at 95% RH, and MCC at the highest at 8.8%. So if we look at the relative change in bulk density at 15 kilopascals normal stress as a function of relative humidity, what I find quite interesting here is that the sorbitol and mannitol both start to increase in density as the sample starts to become more humid, but then that density then drops back down, almost back to the same position where it was at when there was no moisture, or relatively less moisture within the sample. So that there tells us that potentially density could be a misleading indicator of how much moisture is within the sample. Conversely, limestone, we start to see a decrease in density, but then that goes up to a large percentage increase in density towards the end when you go to higher humidities. A couple of the other samples, like the lactose and the MCC, are relatively stable with respect to density. Now looking at the percentage change in basic flowability energy, so that being that the flow energy that we looked at before, so the measurement of torque and force as a function of height, both of which are combined to express a single parameter. What we see here, if we're just focusing on the sorbitol and the mannitol, is that they both follow the same sort of similar path when we're looking at density measurements, but now looking at the flow energy here, we see an increase in the flow energy of sorbitol, followed by a decrease, whereas mannitol follows the opposite trend. We have a decrease followed by a sharp increase. The MCC, which was relatively stable when we were looking at density measurements, actually shows the largest change in the basic flow energy. Goes up to about 50% decrease in the basic flow energy. And if we look at the lactose and the limestone, they actually appear to be relatively stable, so there's not a large deviation in their flow energy as a function of humidity. So what this tells us is potentially that the materials like the lactose and the limestone might flow in a similar manner throughout that humidity range, whereas if we are using materials like the MCC, like sorbitol, like mannitol, we need to be quite careful at what humidity we're doing our measurements at, what humidity we are actually using in process, and make sure that the measurements are being carried out at a similar under similar conditions. So that will allow us to directly understand what's happening in processing. And moving on to the second case study here on caking. During storage, powders can become consolidated, which can then start to lead to caking as the mechanical bond strength between particles starts to increase. And this is often due to water migrating between particles which are next to each other. An example you can see of this on the right hand side of this slide, a graph where we can see the flow energy of a powder increasing over the number of days as caking is occurring, so there's more resistance to flow. And we see that if we add just a 9 kilopascal pressure to that, so 9 kilopascal consolidation, that flow energy rise occurs at an earlier time, so it occurs from about the 5th, 6th day onwards, as opposed to the 6th or 7th day without any load. The way you could see this visually, for example, so here we have some icing sugar that's been stored at different levels of relative humidity, going from 33% all the way to 94%. So as that humidity increases, the powder starts to form agglomerates, so at about 75% RH, before really forming a solid cake, almost solid lumps of material at 94% RH. Caking can also occur with elevated temperatures. So here we've got 3 different polymer samples, polymer A, B and C. We can see that, relatively speaking, in the as received materials all have fairly similar flow energies, polymer C coming in with the lowest flow energy. But as soon as it's stored for 48 hours at 40 degrees, or even when we apply a 2 kilopascal consolidation load to that flow energy skyrockets, and we're almost at 10,000. So on polymer C especially, our flow energy is increased by more than tenfold, and is clearly much more sensitive to storage conditions compared to polymer A, with polymer B coming in the middle. And we can also look at caking with increased humidity as well, so using humidity and time, as we see again. So food materials A, B and C. With food C, we see the steepest rise in the flow energy when we stored at 76% RH for 48 hours. So all those examples there are where caking has occurred uniformly throughout the powder bed. However, that's not always the case. There are many examples of non-homogenous or hybrid behaviours occurring during caking. Other techniques that you might have come across to understand powder flow and to measure powder flow, such as shear cells, penetrometers, uniaxial testing, all require or make an assumption that caking is homogeneous. However, with the FT4, we're able to capture data throughout the depth or the height of the powder bed, so we can then assess the different caking modes that are occurring in different materials. So the first type is homogeneous caking, so that's the example on the left hand side, where we see an increase in energy throughout the powder bed with time, so that the flow energy is increasing uniformly at any given height within that sample. If we move to this middle example, so non-homogeneous caking or crusting, we have a crust propagating throughout the depth of the powder bed. So this peak value is increasing throughout the powder bed, where we then have formed a crust which is moving over time. And lastly, we have hybrid caking, which is where there's an increase in the flow energy within a localized region to start with. So more similar to the crusting example. However, there are also increases in the flow energy throughout the powder bed. So as we go closer towards the base of the vessel, we do also have increases in the flow energy there. So we're getting a mixture of the homogeneous caking and crusting occurring within one sample. And over the next few slides, we'll go into these different mechanisms in a bit more detail. Starting off first with the non-homogeneous caking and the skimmed milk powder at 75% RH. We see initially we have fairly low energy throughout the depth of the vessel. Once we've stored this sample for 1 day at 75% RH, you can see a slight peak forming at the very top of the vessel. As we go down through time, so on the second day, we've got a peak now which is relatively much higher than what we had previously, at about 50 millijoules, and is deeper into the vessel. And as those days continue, we've got now a peak at about 80 millijoules, again deeper into the vessel. What's interesting is that our energy up to that point is now remaining fairly constant. It's not deviating so much. So we've got some caking at the top of the vessel and then a clear crust forming, and the material below that crust does not seem to be affected very much at all. It's still got relatively similar and fairly low flow energies. Going to go to day 5, a very clear peak and crust formation there. And at day 6, we are able to continue that measurement on a bit more and show that the sample has got quite uniform caking above the crust. Moving on to the skimmed milk powder stored at 53% RH, we've got quite similar behaviour. So again, we have a relatively low energies for the as received sample that's not been stored for any length of time at all. A slight peak developing after the first day, and a peak which then develops over days 2, 3, 4. You can see that the behaviour is slightly different in that compared to the 75% RH sample, we had a very well defined peak. The peak here seems to be a bit broader. However, once you do go deeper into the vessel, again, it looks like that the material there is completely uncaked. It's not been affected by the long-term storage. Analysing that raw data in a bit more detail allows us to then evaluate what the depth of the crust is and the energy of the crust as well. So you can see that in both cases, for the 53 and 75% RH, over time the depth of the crust increases, so that the crust is going deeper and propagating deeper into the vessel. And in both cases, the energy of the crust is increasing as well over the number of days, and that increases more so for the 75% RH, which is as you might expect. We can then pull out and evaluate the strength of the crust. So take the energy of the crust divided by depth gives us the strength of the crust. And from that we can then determine if the increase in the energy is purely down to the caked region becoming larger, or if that caked region is hardening over the course of time. So we see that in both cases the strength of the crust is increasing, more so as you might expect for the 75% RH. And so what that tells us is that in both instances the crust is hardening over the storage period. Now moving on to hybrid caking with the sulphonated methyl ester at 75% RH. We can see the as received sample, so on day 0 we've got fairly low energy throughout the depth of the vessel, which is fairly stable. Once we go and stored for 1 day, there's a slight increase in the energy, but there's no clear peak formation that we saw with the sample that was crusting in the last few slides. Once you go to day 2, that peak does appear, so we do have crust formation at the top of the vessel, but we also have an increase in the flow energy throughout the depth of the vessel as well. And that continues as we move on to day 3. We've got clear crust formation again at the top of the vessel and a general increase in energy below the crust as well. And that continues on for days 4, 5 and 6 as well, where we've got a crust forming and caking also occurring below the crust as well. So what we can take away from that is we do have a crust propagating, so we can see that the depth of the crust on the whole is rising as over the storage period, and that energy of the crust is also increasing as well. We also have a rise in the strength of the crust, so that crust is becoming stronger throughout the storage period as well. Now moving on to what we call translational behaviour. So this is a food flavouring sample. Again, our as received sample shows fairly low energy. There's no clear peak in that at all. Once you move on to day 1, we can see a slight crust forming and a general increase in the energy. So that is more similar to what we saw with the hybrid behaviour. Again, we have a slight peak after 1.5 days. But once we move on to days 2, 3 and 4, there's no crust formation at all. That crust has effectively disappeared, and we now have more homogeneous behaviour. So we've gone away from that hybrid behaviour more towards homogeneous behaviour where the whole sample is caked. So that's where we're transitioning between these different caking modes. So as I said, between 1.5 to 2 days, we have hybrid behaviour, and after that point, we move on to a more homogeneous. So with powder rheology, we can also assess the influence of humidity cycling. So understand this complex caking behaviour when a sample is subjected to different levels of humidity. So in order to assess this, samples were stored at 75% RH for 3 days and then returned back to ambient conditions for 3 days. And over the range of samples that we tested, we could see that each one showed a different response to those changes in the environmental conditions. So starting off with flavour 1, so a flavour ingredient, we can see that at day 0, as we've seen before, the sample is exhibiting relatively low energies throughout the depth of the vessel. When we move on to day 3, so this is the sample after it's been stored at 75% RH for 3 days, we have fairly homogeneous caking occurring, and after the 3 days of drying, you can see that there's actually a crust that's been formed. So you've got very clear crust formation after that's formed during that drying time. Moving on to a second flavour ingredient, after 3 days at 75% RH, we've got very clear crust formation. And then once that sample's been dried, we can see that the energy of that crust, effectively the strength of the crust, has been reduced, and we've got a slight increase in the energy throughout the depth of the vessel. So part of that moisture may well have propagated throughout the depth of the vessel, but again we don't return back to the initial state. Now looking at skimmed milk powder, so this is one of the samples we looked at very first, where we had very clear crust formation after 3 days at 75% RH. However, once that sample's dried, we can see that peak has then been dissipated. We've got very clear caking occurring throughout the depth of the vessel, and got caking there occurring below the crust. So it's important here to understand just 3 different samples showing 3 very different types of behaviour when we've returned back down to ambient conditions. So in conclusion, the interaction of powder and the flow of powders when taking humidity into consideration as well is a very complex phenomenon, and that leads to a range of different caking behaviours or different caking modes. So it's not possible just to assume that caking has occurred uniformly, as you might have to do when using different powder flow measurement techniques. But using an instrument like the FT4, the resistance to flow throughout the whole depth of the vessel can be assessed, and by using this type of measurement device, it's possible to understand these different types of caking modes and any transitions between them. Some of the work presented here has also been published in Particulology, which I really recommend that you look up and read. We can send you a link to the paper as well, and has a lot more detail about the different caking modes that have been presented here. So thanks for your attention, and if you have any questions, I'm more than happy to answer them.
Thanks, Rajeev. Great presentation. Always a really interesting topic, caking. So key to many different industries and different applications. So yeah, always a really good topic to learn more about. Hopefully, if I've done this switch over correct, you're there as well. Can you hear me okay?
Yeah, I can hear you fine, Jamie.
Great. Okay. Thanks, Rajeev. So yeah, we've had a few questions come in. So a few along the same topics, but we'll work through the ones that we've got. The first one is, can you just share a bit more information on the salt solutions that we used in the first case study, I think it was, how they were prepared and how long the samples were exposed to the different humidity levels?
Yeah, sure. So the salt solutions which were used, so we had magnesium chloride, which gave a relative humidity of 34%, magnesium nitrate that gave us the relative humidity at 56%, sodium chloride that gave us 75%, and potassium nitrate at the top end at 95%, along with silica gel, which ends up with a low RH at 17%. So all of the samples were held in the desiccator for 48 hours. And the way that the saturated salt solution methodology works is that you create a slurry with distilled water and the desired salt, and that then means that within the desiccator or within any sealed container, you have that level of humidity. But that humidity can vary on temperature, so it is important to sort of that there are tables and things online which you can look up on and work out the humidity with respect to your ambient temperature as well.
Okay, great. Thanks for that. Did you mention then how long they were stored for? Sorry if I missed that.
Yeah, 48 hours.
48 hours. Okay, yeah. So so we had a few questions along those lines, but I think you've addressed all of them in your answer there. So thanks very much for that. Next question is, so you presented, I think in all of the case studies, measurements of flow energy on the FT4. Can you confirm whether that is that the basic flowability energy or the specific energy that was measured?
So the flow energy graphs that I presented, which were as a function of height, were effectively the energy at that height. So it's more like an instantaneous energy. If we were to add all of those energy values up, that would give us the basic flowability energy, which is measured as the blade comes down through the powder. But the graphs where we have, say, that the crusting, which shows when we're 50, 60 millimeters above the base, we have a high energy, and then it drops down. All those are energy values at that particular height. The specific energy is measured as the blade comes up through the powder, which we weren't doing, but for these studies and for this sort of characterization. So for crusting and caking studies, you'd use the downwards energy, the basic flowability energy, but assess that as a function of height as opposed to a single value.
Okay, great. And I think in all of the data that you presented, there was some information there on the repeatability. I think there was error bars on all of the graphs, but perhaps you can just comment on how repeatable the measurements were.
Yeah, so in general, we would have done the measurements in triplicate. For some of the caking studies, we didn't show the repeats on those. It would have been too much data to show in one graph, but we would have had repeats on each of those measurements.
Okay, great, thanks. And again, I've had a few questions along similar lines of this one. How will, in a real world scenario, I appreciate this is a very vague question, but how can caking impact on any process performance? Let's put it that way.
So if you have caking or crusting occurring in a process, it can be important to know exactly with which method that caking or crusting is occurring. So you can, if it's undesirable for that process, you can manage it effectively. So if you know that, say, a crust gets stronger over time, as we saw in some of those examples, and doesn't start to level out and doesn't start to stabilize, then you can know that in process, longer storage periods are going to start to be more problematic. And of course, you can the other part of the study is you can look at different humidity levels. And we saw examples there where if you have samples in different humidity levels,
that can then prevent the crust from, at lower humidity, can prevent the crust from advancing too deeply down into the powder. Doesn't eliminate the problem entirely, but you could know what your cutoff points for the crusting or caking becoming too worse is. You can at least, even if you can't fully control it and prevent it, you can at least use this data to start to manage the problem.
Okay, great, thanks. And again, just an interesting question that's come in, and I guess this is really based on some of your experience in your previous role at Freeman, but have you come across any situations where caking can actually be beneficial?
That's an interesting question. So I think there could be situations where definitely studying caking would be beneficial. When we think about compactions or compacts or tableting, where and especially when you put granulation into that mix as well, we're effectively using water or some sort of moisture or a liquid to bind the particles together, and that effectively is a cake, or to some extent there'll be caking along the way to making a tablet. And so all of these processes are quite intertwined and linked. So the mechanisms that hold a powder together for a tablet are similar and what could then cause caking. So if you have a binder, say, that's used in the granulation process, if that's added to your formulation and then it's stored for a certain period of time, if that binder then starts to form, if that binder then starts to link these particles together, that could then have detrimental effects as we move upstream through the process, and that could then mean that we have more propensity towards caking. Even though we've put that binder in there for granulation, or to aid granulation, it could actually start to form. We could actually start to form cakes and crust. So there are ways in which these sorts of caking studies can help inform other parts of the process.
Okay, thanks. Yeah. So I guess one of the challenges in any kind of formulation or powder handling process is that things like binders or moisture, which could be added for good reason, for example, forming compacts or granulation, are potentially going to give you problems in other parts of your process.
That's right. It might not be expected. It's more likely to be undesirable. But it's important to know that if you add a certain binder, if you add moisture, say, at the wrong point, that could have a knock-on effect, and where you don't expect any caking to occur, you may well then start to get cakes and crust forming, and the powder might start to solidify.
Okay, yeah, great, thank you. Just moving on then through our questions, much more practical one here. So is there a particle size limit to running the caking test? And the person in question here has mentioned they have granular material that's around 500 microns.
So 500 microns is sort of on the edge, obviously depending on the particular vessel size that you have. But there will be ways in which we can work around that with sort of different combinations of vessels and blades. To if there are size limits that we get to, we may well be able to work around that. That's definitely something which the application specialists at Freeman will be able to help with and develop methods for.
Okay, thanks. And again, on a similar kind of vein in terms of the practical setup of the tests, could you just clarify? So in the final case study, I think it was, when you were talking about the crusting investigations, mm-hmm. are the samples stored and humidified within the vessel in which they're going to be tested, so that the crust is preserved?
Yes, that's right. It's exactly that. So the process itself is that the sample is first. So with the FT4, we have a conditioning cycle which will places the sample into a homogeneous condition. So we've got consistent packing throughout the whole depth of the vessel, and we have a known volume of sample. That sample then, in that known state, is then, in ambient conditions, is then placed into the humidity chamber, can be placed into a desiccator, whatever it is that you're using, for whatever time period it is that you're interested in. Then that sample can then be brought back to the FT4. It's not conditioned, and it's using the conditioning cycle from the FT4, but instead we just go directly to a test cycle, which is where we start to measure the energy. So that's how that crust formation is preserved. If you were to do a conditioning cycle, we would start to break the crust, which would render the experiment pointless. So that's why we do the conditioning cycle using the blades on the instrument, store the vessel for whatever length of time in whatever environmental conditions we want, and then come back to the instrument and do a test cycle.
Okay, great. Thanks for clarifying that. And I think probably one final question. Can you comment on how caking investigations vary between what you've shown with the FT4 and also what's possible using a shear cell tester?
Sure. So long-term storage and consolidation measurements with shear cells are fairly common, and you can do times consolidation testing with the FT4 as well, but the shear cell test. But the key benefit of doing these sorts of dynamic measurements with the FT4 is we can evaluate processes like caking, like crusting, and we can find all these different modes of caking, which previously you couldn't assess just using a shear cell. The shear cell requires the powder to become compacted, and we're just measuring the flow effectively on a single plane. Whereas here we're measuring the flow throughout the whole depth of the vessel, so it's more realistic to what's happening in a real life, say, storage situation, or in a real life process where you might have materials in a hopper or a silo, or in big bags that are stored in whatever environmental conditions. And only by doing that dynamic testing can we really find out how the crusting is occurring, if that crusting is reversible, if we move from non-homogenous to a hybrid case, and all these different various modes that we've explored today. You can only find those out using the dynamic methods from the FT4.
Okay, great. Thanks for that, Rajeev. There's one or two other questions that we've had in that are quite specific to certain applications, certain operations. So I think we'll end the questions there, and our application specialists will, if you have asked any other questions, one of our applications team will come back to you in detail on those particular topics. So just to mention as well, one or two people have asked if slides of the presentation will be available. So in the next day or two, we will send out a link to a recording of the presentation, and you can listen to that in your own time, and also feel free to share that with colleagues. You can also access the recording to this and previous events and register for any upcoming events via the website micromeritics.com/webinar. And if you do have any questions at all, then feel free to get in touch with us via info@freemantech.co.uk, or you can visit the website freemantech.co.uk to learn more about the FT4 Powder Rheometer specifically. So with that, just like to thank all of you for your time. Thank you for joining. Hope it was valuable and interesting. Look forward to seeing you all at future events. And also just like to thank you, Rajeev, for your time and for a great presentation. Thanks, everybody.
Thanks, Jeremy. Bye.
Thanks, Rajeev. Bye.